Hi there and welcome. I'm Rebecca Weaver and we're going to look at Chapter 5 today, Applications of the Exponential and Natural Logarithmic Functions. Section 5.1 deals with exponential growth and decay. The definition of exponential growth is a quantity such that at every instant the rate of increase of the quantity is proportional to the quantity at that instant. We say that the quantity is growing exponentially or is exhibiting exponential growth. An example of this would be P of t equals 3 times e to the 4t. Now, if we are looking at exponential growth and we have c and k any constants, and we let y equal capital C e to the kt, then y prime equals c k e to the kt, and that's a solution to that particular function. Theorem 1 is dealing with exponential function solutions of a differential equation, and basically that's what we're looking at here. The function y equals c e to the kt satisfies the differential equation y prime equals ky. Conversely, if y equals f of t satisfies the differential equation y prime equals ky, then y equals c e to the kt for some constant c. Oh my goodness. Let's look at an example and see what in the world that's talking about. So we have the world's population, and it was 5.5 billion on January 1st, 1993. And 5.88 billion on January 1st, 1998. Now assume that at any time the population grows at a rate proportional to the population at that time. In what year will the world's population reach 7 billion? Now, since the oldest information we're given corresponds to 1993, that's going to serve as our initial time. And that's what you're going to do with basically all of these kind of population or time kind of problems. The very initial year that you're talking about, let t equals 0. And the population for t equals 0 is 5.51. And we're going to say that's measured in billions because we don't want to write all those zeros in there. Now, therefore, the year 1998 will be the year t equals 5, which is just 5 plus 1993. So if 1993 is 0, then 1998 would be 5. And the population at time t equals 5 is 5.88, and that's measured in billions. So we have 2 points. Very nice. 2 complete points. Now, since the population grows at a rate proportional to the size of the population, we can use the exponential growth model. P of t equals P naught e to the kt to describe the population of the world. Since P naught is the initial quantity, just plop that 5.51 in there, and our formula then becomes P of t equals 5.51 e to the kt. Now, we can use other given information, 5.88 billion in 1998, to determine k. It's typically what we do with these. And P of t equals 5.51 e to the kt. This is our function so far. Then we're going to plug in when t equals 5. And then we're going to solve for k. Taking the natural log of both sides, we end up with k about equal to 0.013. All right, therefore our formula to model this situation is P of t equals 5.51 e to the 0.013 t. Now we can determine the world's population will be, when the world's population will be 7 billion. What we need to do is we have our derived function, and then we're going to replace P of t with 7, because that's what we want to know when P of t equals 7, and then we're just going to solve that. Dividing both sides, taking the natural log, we're going to get that t equals 18.36 years. Therefore, the world's population will be 7 billion in about 18.36 years after 1993. So that's at about year 2011.36. So around 2011. And we're going to look at our graph next. And there's our graph. And we can see where that population equals 7 billion at that 18 years after 1993. All right, that was exponential growth. Let's look at exponential decay. A quantity such that at every instant the rate of decrease of the quantity is proportional to the amount of that quantity at that instant. P of t equals 3e to the minus 14. Now this is basically going to be the same kind of thing, but instead of our population growing, our population is dying or decaying. Another very common application of exponential decay is radioactive decay. So they're going to show this one first, and this is what we're going to be looking at. You're going to do a few of these in your homework, so I thought we would look at this one. Radium-226 is used in cancer radiotherapy as a neutron source for some research purposes. As a constituent of luminescent paints. Let P of t be the number of grams of radium-226 in a sample remaining after t years, and suppose that P of t satisfies a differential equation P prime of t equals negative 0.00043 P of t. And we know that P naught equals 12. Well, we're going to have to do a few different things here. They're going to kind of walk us into finding some different things. First off, we're going to find P of t, and then we're going to find what was the initial amount, then the decay constant. Basically, they're just walking us through where they want us to go at the end. So finding P of t is what we want to do first anyway. Approximately how much of the radium will remain after 943 years, how fast is a sample disintegrating when just 1 gram remains, and we're going to use that differential equation to get that. Then we'll find what the weight of the sample is when it's disintegrating at a rate of 0.004 grams per year. And the radioactive material has a half-life of about 1,612 years. How much will remain after 1,612 years? And then after doubling that, 3,224 years. All right, so let's go back to the beginning. Since the function y equals c e to the kt satisfies the differential equation y prime equal kt, the function p of t equals c e to the kt equals c e to the minus 0.00043 t, because k is decaying and we have our constant k, which was 0.00043. All right, since the function y equals c e to the kt, c is always the initial quantity at time 0. C is equal to 12 since p naught equals 12. Therefore, our function, you just plop that 12 in for that c, or the p naught, if you will, and p of t equals 12 e to the negative 0.00043 t. Okay. Next, we're given that P of 0 equals 12. Therefore, we know the initial amount is 12 grams. Done with B. C, since our initial decay function P of t equals 12 e to the minus 0.00043 t, the decay constant being the coefficient of t is negative 0.00043. Okay, done with that. To determine approximately how much of the radium will remain after 943 years, we just are going to evaluate the function at 943. So just plop that sucker in there into our decay function. And then we punch the buttons on the calculator. And we get that P equals about 8. Therefore, after 943 years, there's going to be approximately 8 grams remaining. The E part, to determine how fast the sample is disintegrating when just 1 gram remains, we must first recognize that this is a situation concerning the rate of change of a quantity, namely, the rate at which the radium is disintegrating. This, of course, involves the derivative. function. This function is given to us and is p prime of t equals negative 0.00043 p of t. Now we'll determine the value of the derivative at p of t equals 1 when 1 gram remains. So we have our derivative function. We're going to replace p of t with 1, and then we get p prime of t equals negative 0.0043. Well, that was nice. So when there's just 1 gram remaining, the radium is disintegrating at a rate of 0.00043 grams per year. The F part of this, to determine the weight of the sample when it's disintegrating at a rate of 0.004 grams per year, we must determine P of T when P prime equals negative 0.004. Just plop that in for our P prime, solve for P of T, and we get P of T equals 9.3. So the weight of the sample when it is disintegrating at the rate of 0.004 grams per year is 9.3. All right, one more. To determine how much radium will remain after 1,612 years, that is one of the half-lives, we just simply recognize that after one half-life, the original amount of radium will be disintegrated. The original amount was 12. We just say half of that will remain, so we'll have 6 grams. After 3,224 years, that means another half will remain, so half of 6 is 3. And we can verify that by plugging it into our P of T formula. All right, if you have any questions, be sure and let me know. And y'all have a wonderful day. Thank you.